All right, today is lecture number 5. It's actually going to be the last one for our first kind of, like big topic, which is thermodynamics. And from the next lecture onward, we're going to start talking about oscillation and wave, which is going to be sound wave, light wave, or that's going to be until the midterm. Okay, so let's talk about what we covered last time. So last time we talked about a few thermodynamical processes, and of that gonna be for the discussion of heat engine, which we're gonna talk more today. Okay, but before we continue, let's do a quick review. So last time we talked about a few processes, right? So the first one is called isobaric process. So this one is P constant. Okay, so I just gonna write the kind of main point for each process, and if you remember in the last lecture we have a table which lists like the work done, the change in the internal energy, and Q for each process, right? So that one might be handy at some point, so you might want to open that lecture for reference. Okay, but in this case, we have isobaric, which is P constant. This one is kind of like the most, not the most, like the kind of like the more generic process, because like neither Q or W are zero. And then of course you can have the change in the internal energy as well. And the next one is isochoric. So isochoric is V constant. So V constant just means W is automatically equal to 0. Okay, because there's no change in the volume, so the gas does not expand, does not contract. So there's no work done. And the next two are a little bit more important, if you will, because we're going to use this to talk about one particular type of heat engine, which is called the Carnot engine, which gonna, be using these last two processes almost exclusively. So one is called isothermal process. Isothermal is when T is constant. And when T is constant, then the change in the internal energy is also automatically 0, because the change in the internal energy is directly the change in the temperature, right? So if delta T is 0, T is constant, then delta U is 0. The last one is adiabatic process. Adiabatic process is when you have no heat flowing in or out, so Q equal to 0. Okay, so this one is you do anything to the gas and you don't let any heat flowing in or out, right? So think about this as doing the gas expansion or compression in a thermally insulated container. Okay, so that's for Q equal to 0. And some process will have like the formula given. For example, adiabatic process. Remember, what is important is that instead of, well, I can write probably here. So for isothermal process, PV is a constant, right? So if you have 2 points in the isothermal process, for example, well, maybe I'll just write it out just to remind everyone again. So we have a PV diagram, and let's say we have gas starting from this point, and let's say we expand the gas, right? So expand the gas means V gonna increase. So V increase. So that means going to the right like this. Okay. So let's say this is along what we call the isotherm. So that means this process here is the isothermal process. Okay, so along this line. So this line mathematically should be a hyperbola, right? So I didn't draw it to be exactly that, but this is a hyperbola. So you have 2 points. For example, the starting point and the end point, let's call it point 1 and point 2. And it's isothermal process. So if you look at the ideal gas law, PV equal to nRT, right? So isothermal is temperature constant, so the right-hand side is constant. So that means for isothermal process, right? So isothermal, then you can say PV is constant. And because of this, right, this shows that if you plot P and V, then you get a hyperbola, right? But because PV, P times V is a constant, then that means if you have point 1 and 2 here on the PV diagram, so P1, V1 equal to P2, V2, right? So if you know the pressure at point 1 and 2, and then you know the volume at point 1, then you can calculate the volume at point 2 using this simple relation, okay, which is actually follows directly from the ideal gas law, which is this line here. All right, so adiabatic process, again, last time we talked about this, is the process where the change is a little bit steeper than isothermal. So if we start from the first point, same point, number 1, but then now you don't expand isothermally, right? But now you expand adiabatically. The path that you take is going to be a little bit steeper. So you're going to be going down maybe to here, number 3 here. Okay, so let's say this is adiabatic. So it's going to be steeper. And that should be clear to you that it's not going to be at the same temperature at point 1. Because if you want the temperature to be the same as point 1, then you have to stay on this isotherm. But we are not doing that. Okay, so there's going to be the change in the temperature. For adiabatic process, if you remember, I'll write it here. So adiabatic process. So instead of PV equal to constant, well, there's no reason for that to be true any longer because T is not constant. But it turns out that PV to the power of gamma equal to constant, right? Again, this can be, the proof of this can be found on in any textbook that talks about adiabatic process. Okay, and for our case, gamma is just the number 5/3. Right? So we are talking about the simplest case, where the gas we are talking about is called monatomic gas. Right? So maybe this is kind of a side note for any of you who might look into some of the textbook, and it may talk about like different kind of gas. That's gonna be different. So what I'm talking about is this. So for ideal gas, there are kind of 3 categories that we can talk about them. One is monatomic gas. Right. So monatomic, well, mono means 1, right? Atomic is like atom, right? So monatomic gas is the gas that only has 1 atom per molecule. Right. So if you zoom enough into like in individual molecules of gas, you're gonna see the gas just like single particle, like a, you know, ping pong ball, if you will, flying around like this. Okay, and this is not always the case, right? Even though we talk about ideal gas, but ideal gas can also used to describe what we call diatomic gas. Diatomic gas is when the molecule, one molecule of gas actually contains two atoms. So if you zoom in enough, then each molecule is going to look like a dumbbell. And then this thing move around. That's possible to have, right? And well, what determines whether it's monatomic or diatomic? It depends on what kind of gas you have, right? So this is a little bit chemistry coming in here. So monatomic is the molecule that has one atom. For example, that gas can be something like argon gas, neon gas, xenon gas, right? So if you, some of you remember the periodic table of in chemistry, then that's what we call the noble gas. So it's the gas with like the electron shell, which being completely filled. So you only need just one atom to be a stable gas, right? But diatomic gas is the one that needs to have two atoms in one molecule. And actually it's more common to us compared to monatomic gas because 70% of air that you breathe in contains, not oxygen, right? It's actually nitrogen, which is a majority of gas that you breathe in. So 70% of air is nitrogen, 20% is roughly 23 or something like that. I don't remember the number exactly. That's oxygen. Okay, so nitrogen and oxygen are the majority of gas that you breathe in when you breathe, and that's gonna be diatomic gas because if you look at the chemical formula for oxygen gas, oxygen molecule is actually O2. Nitrogen is N2, and even hydrogen is also H2. Okay, so 2 means 2 atoms per molecules, right? So all of these gonna be like a dumbbell shaped molecule if you zoom close enough. So this is called diatomic gas, okay? And what we are talking about in this class, exclusively, we talk about monatomic gas because this is the simplest to calculate, to talk about. So what's the difference when you have diatomic gas? Well, if you have a dumbbell, then you must talk about the rotation energy. You must talk about the vibration energy because the dumbbell can, it's kind of like a spring connected to kind of atom together, so it can vibrate like this. And vibration also requires energy, right? So you need to talk about the vibrational energy, you need to talk about rotational energy. So the discussion is a little bit more complicated. So that's why we are not talking about diatomic gas in this class. So we talk about monatomic gas exclusively. And if you talk about diatomic gas, for example, in some other class, then the value for gamma here will also be different. Okay, so strictly speaking, gamma equal to 5/3. This gamma that appears on the adiabatic formula, that only applies to monatomic gas. Okay, and well, since in this class we only deal with this, so you can just take this to be exactly 5/3. But just keep in mind that it might not be always true if you talk about different kind of gas. Okay, and well, since we are talking about this, let me talk a little bit about the last type, which is polyatomic gas. And some of you probably know that there are many other kind of gas which contains more than just 2 atoms. For example, water vapor, right? Water vapor is also a kind of gas that contains 3 molecules, okay? And also if you talk about methane, right, That's 5 molecules. So this one is even more complicated because the way it can rotate, the way it can vibrate, can be a lot more than just diatomic gas. Okay, but anyway, we're gonna talk mostly about this monatomic gas. Okay, so this one is kind of like, a side note, if you will, just to clarify, because in the textbook, most of the textbook will go a little bit deeper than what we talk about in this class. So you know that what we mean by diatomic gas, polyatomic gas, and monatomic gas. Okay, so I hope this is clear to everyone. So this is what we talked about in the last lecture, and as kind of like a prelude to the topic that we're going to talk about today, we're going to do a quick problem, okay, just to make sure everyone is on the same page. And then we're going to start talking about the heat engine today. Okay, so I have a very simple problem here, which is a PV diagram. And the thing is that we are trying to reach point B starting from point A. And then you can see that we are taking two different paths, right? First going up and then go right. That's what we call the A, B, D path. And then the other path that we can take is A, C, D, right? So go right first and then go up. And you can see that these two paths, even though it starts at and ends at the same point, they're going to give different value for work and heat. Okay, so this is kind of like a simple example that demonstrates what we have been talking about so far. All right, so let's try to do this. So in the process AB, which is this one, going up straight, this one does no work, right, because there's no change in the volume, right? So 150 joules of heat is added to the system. Okay, well, that's responsible for going up here, because going up, you probably need to increase the temperature of the process, right? So where do you get that energy from? Well, you get that from heat here, 150 joules. So from A to B, so let's just write it here. So Q from A to B, you add 150, so let's just write plus 150 joules. And then from B to D, more heat is added. So Q, B to D, how much do we add? Well, we add 600 joules, so that's another plus 600, okay? But then from B to D, you do some work, right? So the work done from B to D is no longer 0, even though from A to B is 0, right? Because the area under the curve is 0. So what's the work done from B to D? Well, that's just the area under the curve, so it's going to be the shaded area here, right? So that's going to be the work done. And that's rather easy to calculate, right? Because it's just base times the height. And the base is just, well, just write it P times delta V. So that's going to be the pressure, which is 8 times 10 to the 4 Pascal. That's P, right? This value here. Times delta V, which is 5, well, 0.0 minus 2.0 times 10 to the minus 3 meter cube. Okay, so I'm not writing the unit because everything is in SI unit already. Okay, so if you calculate this, so that's going to be 3 times 8. So that's going to be 240 joules. And it's positive because the volume increases. Okay, so all of this gonna allow us to calculate what is asked in the first question. What's the internal energy change in the process of A and B? Well, okay, not really, because we are a little bit ahead of the question. But for A, the internal energy change A to B, which is this one, well, the work is 0, right? So everything you put in terms of heat, gonna appear as the increase in the internal energy, right? So for A, since W, work done A to B, is 0, so delta U is simply Q, right? So that means delta U from A to B is also plus 150 joules, right? Because it's already given like this. Okay, so you can calculate delta U also using this formula 3/2 and delta T, something like this, right? But this one is a lot cleaner, because for this one you need to calculate the temperature here and calculate the temperature here, and then you have to subtract them, right? So it's gonna be multiple steps, but we don't need to do that since we know that work is 0. So everything you put in must be increase in the internal energy. So the green problem, the answer is 150, right? The next one is the internal energy change in the process ABD. So it's going up and then to the right, like that. Okay, so we can do the same thing as we did before, right? So so delta U from A to B to D is essentially Q from A to B to D minus work from A to B to D. Okay, and well, you can, well, there are actually 2 ways to do that. You can just do the point here, which you already calculate from the earlier problem, or you can just do one at a time from the beginning. That's what I'm gonna do here. Right. So Q from A to B, that's 150, and then from B to D, that's 600. So altogether, you add heat for 750, right? So make sure you understand where this number comes from. So 750. So that's coming from adding these 2 numbers together. And then minus the work done from A to B and then to D, right? But A to B is 0, so we only need this number. So that's going to be minus 250 joules. So altogether, it's going to be 510 joules. So that's going to be the change in the internal energy. Okay? A to D. And then the last one is actually the most interesting one. Last one is total heat added into the process ACD. So it's the bottom process here, ACD, right? So what's the heat done? The heat added. Well, it's more interesting because heat added is given in the previous problem, right? For A and B is given. So now you're asked to calculate. So you have to think a little bit about like how we can use the information that we have earlier to calculate this. Well, before you can do any calculation, let's just write down the formula. So delta U A C D is the same as before, right? Except you are taking different parts, so it's ACD, QACD minus W ACD. Okay, and Q is what we are trying to find. So let me just write Q because we know what we are talking about. And then minus the work done, ACD. Well, the work done from A to D, going through part C, that's only this area here, right? Because from C to D, there's no area. So the work done is 0, right? So you only need the area of this rectangle to write down the work done. So that's going to be just 3 times 10 to the 4 Pascal times the change in the volume, which is 5 minus 2 times 10 to the minus 3 cubic meter, right? So if we crank the number, then you get this part to be 90, right? So it's Q minus 90 joules, right? What about this? Do we know this? Well, yes, we do, because remember that delta U does not depend on the path that you take, right? So as long as you start from A and then end up at D, delta U is going to be the same, right? So that means we can just take delta U from the previous question and then substitute this into the left-hand side here, right? It's going to be the same number, even though it's different path, but delta U is path independent. So we can write this to be 510, right? So Q is simply 510 plus 90, so that's going to be 600 joules. Okay, so you can see that the path that you take down here and then up, right, it's going to be different in terms of the heat added into the system, because the yellow part takes heat of 750 joules, but the one down here is 600 joules, right? So you can see that Q and W depends on the path, but delta U is independent of the path. Okay, so this is a simple example that you can calculate rather comfortably after we have talked about these since last time. Okay, so what are we going to talk about today? Well, we're going to talk about, so let me go back here. And so today we're going to talk about, first of all, the heat engine. We kind of talked about that a little bit last time, at the end of last time already. So heat engine. And then we're going to talk about a reverse of the heat engine, which is the refrigerator or air conditioner, right? And then entropy and second law of thermodynamics, okay, which is not F equal to ma, by the way. That's second law of Newton's law of motion. This is not that. And then the last thing we're going to talk about is what we call Carnot engine. Carnot is the name of French physicist, which actually lived many years ago, like I think 200 or 300 years ago. And it's one of the few cases where his study still kind of relevant nowadays. That's not always the case for physics, because the knowledge of physics evolves all the time. And most of the stuff which is older than a few hundred years should be like obsolete, but this is not that. So Newton is also like that, right? Nowadays we still use Newton's law to calculate anything which is not requiring quantum mechanics. Okay, so let's talk about the heat engine. So the heat engine, like we said last time, is just an engine that operates between two temperatures, right? So it operates between two temperatures, and those two temperatures are kind of controlled or set by what we call the heat bath. Okay, and the goal of the heat engine is trying to extract work, right? So goal is to extract work from these two heat baths, these two temperatures. So let me just say heat bath here. And then we can use work to do anything we want, right? To drive a car, to fly an airplane, to generate electricity. Okay, so work is what we want. A typical kind of diagram that you can see in terms of the heat engine can be shown here, right? So let me explain like what this means, and then we're gonna talk about the next thing, which is called the efficiency of the engine. Okay, so you have two heat baths. One is the hot side, so usually we place that at the top, and then one is the cold side, which we put that at the bottom. Okay, so in this case, it's not shown in the diagram like how hot is the hot side. So the hot side can be, I don't know, like let's say 350 Kelvin, right? So that's a little bit hotter than today outside temperature, but it's fine. And then the cold side might be, 300 Kelvin. Well, as long as the cold side is colder than the hot side, it should be fine. Okay, but it's not specified here. But what we are seeing here is that in order to extract work, W out here, which is again what we want, we need to suck some heat from the hot side. So that's going to be 100 joules here. Okay, so the heat from the hot side will flow from the hot side, flow out from the hot side, right? So you can also write this to be QH, right, to indicate that this is heat that you extract from the hot side. And then some work can be gained from this heat, but the thing is that you're not going to get all the heat that you extract from the hot side and convert that into work, right? So we're going to see why that's not possible in a few moments. But any heat engine, you have to dump some heat back into the whole side. So that's going to be QC. Okay, so for heat engine, the flow of the heat is always like this. All right. So we are not going to be that explicit in terms of the sign. Okay, so we're not going to say that QC is minus 60 or something like that, because that's going to be very confusing. Okay, so we're going to always use positive number, but it should be clear to everyone that QH is the one that flow out from the hot side, and QC is the one that you dump into the cold side. If we talk about a refrigerator, then it's going to be in reverse. Okay, but let's talk one at a time. So this is a heat engine. Okay, so now you get 100 from the hot side, and then you throw away 60 joules to the cold side. Right? It should be obvious to you that the work that you get here should be 40 joules, right? And that's just coming from the conservation of energy, right? You get 100, you throw away 60, you have 40 left, and then you can use that for work, right? So that's kind of nothing you can do much about that. It's not possible for this to be 50, because then you're going to gain more than you get. That's in violation of conservation of energy, right? So that's not good. Okay, so that's fine, and let's kind of write down the work done in all of these, right? And basically just subtracting number. Okay, so this one is 200 out to 160 being dumped into the cold side. So this one again is 40 joules. And next one is 90 minus 60, so that's going to be 30 joules. And the last one is 90 minus 40, so that's going to be 50 joules, right? So it's very easy to calculate how much work you're going to get from this kind of diagram, right? But that's not quite as interesting as asking, okay, we have this 4 different kind of engines, right? Which one is the best in terms of the efficiency, right? So that's the next thing we're going to talk about. So we're going to talk about the engine efficiency. So efficiency. So what is efficiency? In terms of the engine or kind of mechanical device, is usually defined to be what we want divided by what we need to pay. And this kind of definition actually applies to anything, right? When you, let's say, you go to a department store and then you want to eat some or drink, right, some bubble tea, and then you have, like 5 stores that sells. That's not exactly the same thing, but it's the same kind of product, right? So then, which one gives you the best bang for the buck, right? You need to say, okay, what do you want? Well, you want bubble tea when you want a lot of them, and then how much do we pay? So you kind of like do this kind of, comparison, and the one that has the best is you get most from what you pay, right? So that's going to be the best efficiency. So in this case, what do we need to pay? Well, okay, before that, what we want is clear. We want the work done. So that's going to be always what we want. So W is the thing that we want. So what about the denominator, what we pay? Well, what do you pay is the amount of work or amount of, not work, amount of heat, which is the energy that you draw from the hot side. So what we pay is the QH. Okay, what we pay is QH. So this is a very kind of simple definition of efficiency of a heat engine. And using this, then you can calculate the efficiency of each one using this formula. So efficiency is kind of long, right? So sometimes we use like this kind of curly E to indicate the efficiency, right? So efficiency of the one on the leftmost, that's going to be work, which is 40, divided by what we pay, which is 100. So that's going to be 40% efficiency. Now for the next one, you get the same amount of work. So you might think that it's going to be as good compared to the first one. But you see that in order to get 40 joules, you need to extract more energy. So that should be clear to you that the efficiency is worse compared to the one before, because now you have like 200. Now we have 40, but then you need to divide by 200 because 200 is what you need to pay. So the efficiency is half what we had before, which is only 20%. Okay, and the rest follows the same pattern, right? So the efficiency for the third one is what we get, 30 divided by what we pay, 90. So that's going to be about 33%. And the last one is 50, what we get divided by 90, right? And then this one is about 56%. So the last one actually gives you the highest efficiency in terms of the heat engine, right? So to get the same amount of work done, then you extract less energy from the hot side. Okay, so because of the conservation of energy, remember how we calculate work in the first place? We just take this one and then subtract that away from QH, right? So sometimes the formula for the efficiency can be written to be, well, W, what is W? W is just QH minus QC, right? I'm putting the absolute sign again to eliminate all the ambiguity in terms of the sign, right? So just take the number and then subtract them, just like what we did earlier, and then divide by QH, right? So with a little bit of tidying, you can also write this in terms of 1 minus QC divided by QH. Okay, so all of these are the same formula for efficiency. It's just expressed in a different kind of like, presentation. But I mean, you don't have to remember like all of them. The only thing that worth remembering is this one, right? Because work can be calculated from the difference of the heat QH and QC. Okay, so far so good. So now you can ask something like this. Is it possible to have 100% engine in terms of the efficiency? For example, why do we need to throw away heat to the cold side? Why can't we just, take everything from the hot side and then just put it into work? So 100 joules extract from the hot side, and we get 100 joules as work done. Why is that not possible? To answer that, we need to step back a little bit and talk about the other concept, which is also very important. Actually, in terms of like the foundation of physics, is probably even more important than the first law of thermodynamics. Okay, so we're gonna come back to this diagram later. After we talk about the next thing, which is the entropy. And so let me do that. So we're gonna talk about the second law of thermodynamics. Second law of thermodynamics. Okay. So there are many ways to state second law, but all of them are equivalent. So we're going to talk about just one particular kind of way of saying what the second law is. So in order to talk about second law, we have to talk about the new concept, which is called entropy. But before we talk about what it means, let's just say what the second law is. So second law says that the change, or not the change, well, the entropy of a closed system cannot decrease. Okay, so it's a very concise statement that contains many kind of hidden definition in it. Okay, so let's talk about what it is. So what is the entropy? Entropy is the quantity, which is usually we talk about the change in the entropy, not the absolute value of entropy. So most of the time you're going to see it to be written in terms of delta S. Okay, so S is the entropy, right? Which is kind of, I don't know, strange because there's no S in the word entropy, right? But anyway, that's what people use. So delta S is defined to be the amount of heat divided by the temperature. Okay, so this is the definition. So so what it means is that, so in terms of like exact example is, let's say you have like a heat bath, which is, let's say, at 300 Kelvin, right? And let's say this heat bath lose heat by, let's say, 10 joules, right? So let's say it's extracted from the hot side by 10 joules, right? So in this case, Q is flowing away from this heat bath, okay? So in this case, Q is going to be minus 10 joules. or delta Q if you want. Or Q or delta Q doesn't really matter much in this case. So delta S is just delta Q divided by T. So in this case, it's going to be minus 10 because you lose heat. Right? This is from the point of view of the heat bath. And divide by the temperature, which is 300. Right? So what it says here is that this heat bath has entropy decreased by this much. Right? So it's minus 10, 1 over 30 joules per Kelvin. That's the unit for entropy. So entropy decrease in this case. Right? So that's kind of like the meaning of the first word, the entropy, right? Delta S is delta Q divided by T. And then the next one is, what does it mean to be a closed system? A closed system is a system where nothing can leave and nothing can get into the system. That includes the energy, that includes the, the number of particles, something like that. Right? So the closed system is the system where nothing can leave the system and nothing can go into the system. And usually we're going to talk about energy flowing in or out. Right? So a closed system, all the energy is contained within the system. And then the last thing is the term which says cannot decrease. Cannot decrease means it can stay the same or it can be higher than before. It can increase. Right? So all of this can be written in one very simple inequality, which is something like this. So delta S of a closed system, which is the change in the entropy of a closed system, must be larger or equal to 0. Okay, so this line and this line here, they mean the same thing, exactly the same thing. Okay, and we're gonna see how we can use this to describe some of the things that you encounter in daily life. For example, you always see heat flow from hot to cold. Why cannot heat flow from cold to hot? Even though you're not violating conservation of energy, that never happens in real life. So why that's the case? Okay, so we're gonna take a quick break here, and then we're gonna continue after the break and use this second law of thermodynamics to show why that's the case. Okay, so let's take a quick break here. So let me set the timer, and then we will come back in 10 minutes.